The last learning objective in ESS1-4 is number 5. I can predict a change in orbital period for a given change in orbital radius. So this would be like, let's say the radius doubles. How would the period change? Now, for planets, this is a silly question because a planet isn't going to suddenly become twice as far away from the sun as it was before. However, for smaller objects such as comets or satellites especially, this is an important question. Satellites, let's take that for example. A satellite is a man-made object we put into space, or that's what we're calling it. Technically, a satellite is anything that orbits another body. So even the moon is technically a satellite. However, colloquially, we don't call the moon a satellite. When we say satellite, what most people are talking about are man-made objects put into space orbiting the Earth. So we put an object into Earth's orbit, but what if we wanted to have this object be further away for one reason or another? So we change its orbit to be further away. That's going to have a corresponding change in the period because of Kepler's third law. So let's calculate how much change would occur because we've changed the radius. And this type of physics problem where we're changing one variable and seeing how the other one changes is very common. So I'm going to teach you an approach I like to use to solve any kind of problem like this. So the first question is, how would the period change if the radius doubled? So simply multiply the radius by 2. What happens to period? Let's start with Kepler's third law. And what we're going to do is, notice that here we have the radius cubed. What we're going to do is replace radius cubed with 2 times the radius, all of which is cubed, and that's important. You don't just put a 2 in front of it and not cube the 2. The 2 gets cubed as well because we're replacing one r with a different r, for example. In fact, we can label this. So let's say this is the initial r, and then this is the final r. So let's say this is the initial r. This would also be the initial r, but what we're saying is that the final r is equal to 2 times the initial r. So we're replacing r with twice the r. And then we're going to distribute this cube into both factors. And so we have 2 cubed is 8 times r cubed. And then since multiplication follows a commutative property, meaning we can reverse the order or change the order of multiplication, what we're going to do is we're going to take that 8 and just bring it to the front. So now we have 8 times the rest of Kepler's third law. Now, doesn't that part right there look like what Kepler's third law originally states? So it looks a lot like what period squared is. So instead, what we're going to do is replace all of this right here with period squared, but label it period 1. So initial period, a period we would have had we not doubled it. So what we can do is go back up here to this initial period and label this 1. And then what we're doing is we're finding, okay, now we have a different period because we've doubled the radius. How does that different period, that period 2, compare? So period 2 squared is equal to 8 times period 1 squared. It's a little bit easier to understand if we remove the squares, so we're going to square root both sides. And in the end, what we get is that the second period, so the period after you squared the radius, is equal to square root of 8 times the original period. So if the original period is 1 year, 1 second, 1 something, we have square root 8 times that. So it would be square root 8 years instead. So let's just once again go over the trick that we have used. We have written the original equation, labeled our variable with a 1, then made a change to the variable that we are changing, in this case the radius, doubling it, and substituting in 2 times the original radius, and labeling this as a different period, rearranging the equation such that we get back what we started with, and then substituting in for that the original other side of the equation, the period, the first period, squared, and so that we have some kind of multiple times a period equals some other period. That trick can be used for most anything. If we go back to our kinematic equations, I could ask the question, okay, how would the distance traveled change if you double the initial velocity? And so you'd make 2 times the initial velocity, and then you would rearrange it to look just like it was before, and then answer the question of, okay, well, how would it change? Well, by what factor would it change by? So I'll leave you with a practice. So here's the practice for the notes. An asteroid is flung into a new orbit because of a close encounter with a moon. So in other words, we had a three-body problem situation where we had three objects all exerting gravitational attraction, and it caused the change in an orbit of one of the objects, in this case, an asteroid. That happens plenty of times. Asteroids can get flung into new orbits. So with this new orbit, we're going to say the orbit is 4 times larger in radius than the old orbit. How does the period or orbit change? How does the period of the orbit change? So go ahead and complete that one. Use the same trick that I taught you. This time it's 4 times larger instead of doubling.